In this lecture of signals and systems, we are going to discuss continuous time signals and discrete time signals. A continuous time signal or CTS is a function of the independent variable time t, and it is defined for all the values of the independent variable t. Continuous time signal can be represented by xt, where x is the dependent variable and t is the independent variable. For continuous time signal, the independent variable t is continuous, that is, it can take any value on the real axis or in the x-axis. So for the continuous time signal, we can write t belongs to the real number r. There can be more than one independent variable, but the signal which is defined by xt depends on only one variable t. The continuous time signal xt can also be represented graphically. Let me take an example of this continuous time signal. For the graphical representation of the continuous time signal, the independent variable t is defined in the x-axis and the signal amplitude is defined in the y-axis. Let's take a signal which is defined by xt is equal to t, which is basically a y equal to mx line with the slope m equal to 1. As we can see, this signal xt is defined for every values of the time t, or this signal is a continuous signal with a time t. Let's take another example. Like previous, we have an independent variable t which is defined in the x-axis and the signal amplitude which is defined in the y-axis. Let's take a signal with the amplitude p from t is equal to 0 to t is equal to a, and from t is equal to a to plus infinity, the value of the signal is 0. Again, from t is equal to 0 to t is equal to b, the amplitude of the signal is p, and from t is equal to b to t is equal to negative infinity, the amplitude of the signal is 0. So the amplitude of the signal is p from t is equal to b to t is equal to a, and for other instance, the amplitude of the signal is 0. As we can see, this signal is also defined for every values of the time t in the x-axis. That's why this signal is also a continuous time signal. Discrete time signals. A discrete time signal or DTS is a function of independent variable n in the real axis or x-axis and defined for the discrete values of the independent variable n. Generally, the discrete time signal can be represented by xn, or x is the dependent variable and n is the independent variable, and this n is an integer. This xn is also known as sequence. It is usually generated by sampling of the continuous time signals so that it only has values at the equally spaced time intervals in the time axis. So for the discrete time signal, this independent variable n belongs to z or integer numbers. Now, as the discrete time signal is the result of the sampling of the continuous time signal and defined for the discrete values of the independent variable n, let's take a continuous time signal which we have previously discussed. For generating a discrete time signal from this continuous time signal, we need to define the value of this continuous time signal at discrete time instants. Let's take the sampling instance. The signal is xt is defined at t is equal to 0. In the positive x-axis, the sampling instants are t is equal to t0, t1, t2, and all the way up to tn. In the negative x-axis, the sampling instants are t is equal to minus t1, minus t2, and all the way up to minus tn. So we take the sample of this continuous time signals at these instants, or the signal xt is defined at time t is equal to 0, which is equal to t0, and time t is equal to t1, t2, and all the way up to the tn in the positive x-axis, and time t is equal to minus t1, minus t2, and all the way up to the minus tn in the negative x-axis. Or the signal xt is not defined for every value of the time t. So if we want to determine the value of xt between t1 and t2 or any other two consecutive integer, then we cannot do it, as the value of xt is not defined for every time instance. Let's plot the discrete time signal. In the x-axis, we will take the independent variable t in the discretized form. In the y-axis, we will take the amplitude of the discrete time signal xn. In the positive x-axis at t0, t1 and t2, the value of the signal is p, and from t3 up to tn, the value of the signal is 0. In the negative x-axis at minus t1 and minus t2, the value of the signal is p, and from minus t3 up to minus tn, the value of the signal is 0. The discrete time signal can either be equally or not equally spaced from each other. The spacing between the sequence is known as time interval. So we can define the time interval for DTS as the time interval is defined as the time difference between two consecutive time instants. If we take two consecutive time instants t1 and t2, then the time interval can be given by t2 minus t1. This time interval determines whether the signal is uniformly sampled or not. If the time interval for all the consecutive time instants is same, or del t is equal to t1 minus t0, which is equal to t2 minus t1, which is equal to t3 minus t2, which is equal to all the way up to tn minus 1, then this signal is uniformly sampled. If the time interval for all the consecutive time instants is not same, or del t is equal to t1 minus t0, which is not equal to t2 minus t1, which is not equal to t3 minus t2, up to tn minus 1, then the signal is not uniformly sampled. When we create a discrete time signal by taking the samples of the continuous time signal, then the obtained discrete time signal independent variable in the x-axis will be same as continuous time signal, or both will be defined in the time domain t. Again, we have seen that for the discrete time signal, independent variable in the x-axis is the integer variable n. So how do we get the integer variable n from the variable t in the x-axis? For this case, we will consider the equal time interval between the sequence. Let's say the time interval between the two consecutive time instants is equal to capital T. So t1 minus t0, which is equal to t2 minus t1, which is equal to t3 minus t2, up to tn minus 1 is equal to capital T. Identify this as equation number 1. If t0 is equal to 0, then t1 minus t0 is equal to t1 minus 0, which is equal to t1. Similarly, t2 minus t0 is equal to t2. Now from equation 1, we can write t1 minus t0, which is equal to t1, can be replaced by capital T, as the difference between the t1 minus t0 is t. Similarly, t2 minus t0, which is equal to t2, can be replaced by 2t, because t2 minus t0 is equal to t1 minus t0 plus t2 minus t1, and both are equal to capital T. Similarly, t3 can be replaced by 3t, because t3 minus t0 is equal to t3 minus t2 plus t2 minus t1 plus t1 minus t0, which is equal to 3t. Similarly, t4 by 4t and tn by nt. So the independent variable t in the x-axis can be replaced by nt, and the dts can be represented by x and t. And if we cancel out t in the plot of x and t, or consider t is equal to 1, then it will become 1, 2, 3, 4 up to n. And nt will become n, or x and t will become xn, where n is equal to 1, 2, 3, 4 up to n. Let us see the different representation for the discrete time signals. Representation of the discrete time signals can be done by using graphical representation, functional representation, tabular representation, and sequence representation. We have already seen the graphical representation of the discrete time signal. Let's take an example of the discrete time signal and see the following representations. Let's take a signal xn. The value of the signal xn at 0 is 1, at 1 it's 3, at 2 it is 1, and at 3 it is 2. And in the negative x-axis, the value of the signal xn at minus 1 is equal to 2, and at minus 2 it is minus 3. At first, let's see the graphical representation of the discrete time signal. Like previous, in the x-axis we are going to take the integer values, and in the y-axis we will take the signal amplitude. This signal has a value of 1 when n is equal to 0, 3 when n is equal to 1, 1 when n is equal to 2, and 2 when n is equal to 3. When n is equal to 4, the value of the signal xn is 0, 2 when n is equal to minus 1, and in the negative x-axis 2 when n is equal to minus 1, minus 3 when n is equal to 2, and 0 when n is equal to minus 3 and minus 4. So this is the graphical representation of the discrete time signal xn. Now let's see the functional representation of this discrete time signal. For this representation, the signal amplitude should be written against the value of n, or it can be represented as minus 3 for n is equal to minus 2, 2 for n is equal to minus 1, 1 for n is equal to 0, 3 for n is equal to 1, 1 for n is equal to 2, and 2 for n is equal to 3. Tabular representation. For this representation, sampling instant and their corresponding amplitude is written in the form of a table. Sequence representation. For this representation, the amplitude of the signal is written inside the curly braces, and the signal at n is equal to 0 is denoted by an arrow mark. The left side of the arrow mark is for the negative values of n, and the right side of the arrow mark is for the positive values of n. And for this signal, the value of the signal at n is equal to 0 is 1. That's all for this lecture. If you have any doubts regarding this lecture, then you may ask it in the comment section, and don't forget to hit the subscribe button. See you in the next one.